Good afternoon, ma'am. Can we wait for 3-4 minutes as the participants
No
have checked?
problem, no problem, no problem. But can you just, I will just share my thing. Can you just see whether it is visible or not?
Yeah, you can try.
I will check it. Huh? Is it visible? Hello, the screen is visible to you?
Yes.
Yeah, it's visible.
Yes, ma'am, yes.
You just need to make it full screen.
Slideshow, just put slideshow. Yes, perfect, ma'am. Perfect, madam.
Okay, fine.
Yeah, now it's perfect.
Very good of everybody.
Sorry, ma'am.
Very good afternoon to everybody.
Yeah, good afternoon to you as well.
Thank you, madam.
Yeah. Hopefully I'm audible.
Yeah, now
Yes,
it's
yes,
perfect.
clear now.
Yeah.
So should we start or we should wait for 1-2 minutes as well? Mahesh?
Yeah, we can start now because
So,
time is 2:30.
mhm. Okay, so dear participants, good afternoon to everyone, and let me welcome you again on the second day of this workshop. I hope you are enjoying this workshop. As usual, I ask participants kindly mute your audio, and if you have any questions during the presentations, please type them in the conversation or chat box. And at the end of session, we will bring this question to the speakers, and then we can have a short discussion. Now allow me to introduce our first speaker of the day, Professor Devshani Chakravarti. Professor Chakravarti obtained her PhD in mathematics from Department of Mathematics, Indian Institute of Technology, Kharagpur. She is the nominated member of Indian National Academy of Sciences, Allahabad. She got Young Scientist Award in Mathematics by Indian Science Congress Association and the Young Scientist Scheme from Department of Science and Technology, India. In addition, she got research associates and fellowship from Council of Scientific and Industrial Research, New Delhi. She also got Best Presentation Award from International Science Council, London. The author of 2 books and more than 130 research papers to date, her scientific interest includes multi-criteria decision analysis, fuzzy optimization, fuzzy logic and approximate reasoning. Her research Her recent research direction includes fuzzy geometry. So now with further delay, I would like to hand over this session to Professor Chakravarti. Welcome, ma'am.
Very good afternoon to everybody. Hopefully, I'm audible clearly to you, all of you. Now, my today's topic is, let me just share it first. My today's topic is Introduction to Fuzzy Geometry. Now, on this topic, I started working since 2011, but I do work on fuzzy optimization. But while I was applying fuzzy theory in optimization, I faced certain problem in the sense that I wanted to just the frontier of the in an optimization. I want enough, and I wanted to see how it is being and in fuzzy environment, etc. In my just declare that this is coefficients of a function as, and we work with the C values only, but how really it is interacting in the at the time of optimality, that was my main question. That's why I will just mention a few where I stuck and I started my work on fuzzy geometry that I will tell you. Now, this is this is a simple model for multi-criteria decision making, where we are having several objectives. Now, from the left-hand side space, that is the decision space, we are mapping to the objective function space. This is the general idea for any multi-objective problem. And we are trying to find out the non-dominated frontier for this. Now, this is non-fuzzy. I could see the non-dominated frontier consists of a curve, simple curve, where there is no haziness at all. And I could just discuss each and every point of that. Therefore, finding out the parameter optimality for multi-objective and optimality for the single objective won't be a problem for me. I could visualize everything here. But let me take one example, that minimization of x square, and simultaneously we are just minimizing x minus 2 whole square together. Now x is in between minus 4 and 4. Now there are two curves there. We are trying to find out the parallelograph for this problem. Because this is a multi-objective, there is a trade-off between the objective functions. That's why we won't get the optimal solution for the both together. We will search for the parameter optimality. Now you see in the fuzzy environment the same problem, how it looks like. Instead of taking the coefficient of x as 1, here I have taken simple fuzzy one, which boundary over 1. Now you could see the same curve is transforming from here to here. Now the parameter optimal frontier, you could see this is a hazy boundary. Though I have just clearly I have written the 4 point and the extreme, the curve at the 0 level, but still the parameter frontier is fuzzy in nature. This is another problem. Just I wanted to convey to you that where the problem is coming. Now here also the same problem. How to find out the parameter optimal frontier for this multi-objective problem. Therefore, you see this problem is becoming, if there is no fuzziness with the red colored curve, I could say that this is the parameter front, which is the combination of different points together. But once it is becoming fuzzy, you could see the transition from non-fuzziness to fuzziness, the boundary is becoming a fuzzy boundary. Therefore, finding out the parameter optimal frontier would be a really hard task for anyone to get it. From here, my journey started with fuzzy geometry. Because as you know, while we are doing the optimization, we are come across different kind of mathematical operations, differentiation for finding out the tangent at a point, normal, etc. If the boundary itself not clearly defined, then how really to get one tangent? Rather the first derivative at the boundary of the region. That's why I thought, let us try to see how it looks like. See, this is a combination of different fuzzy points. Now I started looking at the literature for this, and I could see there are really a very less number of works are there on fuzzy geometry. It was started in 1997. Buckley and Islami, they just defined fuzzy point, fuzzy circle, etc. But there was no closed form of now, with mathematicians, we are working with any function, we are interested to find out the closed form because without that, we cannot do distinction. Cannot very difficult. I period for fuzzy geometry has not been it height with distance of as we do increase and it lacks inner conformity. That means when using the definitions in our classical geometrical sense, we are not able to reach to our standard Euclidean geometry. Now I started thinking about it. Now Professor Jade has said that any fuzzy curve is a transformation, rather the counterpart of a crisp curve, and it is formed by a fuzzy transformation over the curve C. How it looks like? He also mentioned that it is, if we just draw the transformation with a spray pen, then it will just look like a hazy curve. For example, if I just put a ink pen on a blotting paper, the paper just takes the ink and sprays in the surface. But you see, that's the hazy curve. Is it really fuzzy at all? Because we know the fuzzy in the sense that there is a clear idea of the transition from the membership to non-membership function. That's why spreading in a way does not really reflect the curve at all. But this is the idea how we can visualize. Now, let us, this was the definition given by Buckley and Islami in 1997. You see, here we have defined a fuzzy point in an Euclidean space, simple space where x-axis we have taken the value 1 and in the y-axis we have taken the value 3. Now, why I was thinking about the fuzzy geometry, 2 points came in my mind that whether to consider the considered scale, considered axis as a normal Euclidean axis or whether the points are within the axis and itself fuzzy numbers. Now, you see, universe is always non-fuzzy. As we know, universe is certain always. In probability theory also, we say the same thing. The way we perceive the event, that is fuzzy. Why it is so? Because there is a difference in perception between you and me, difference in understanding, difference in representation. That's why the whole cognition process reflects in defining the membership function of any fuzzy event. That's why I just took the scale as the normal Euclidean scale where the universe is crisp in nature. Now, we have defined a fuzzy point here. Now, how it looks like? It looks like at points 1 and 3, the intensity is more, the black color is more, that means the membership value is 1. Now, once we are fading, we are going out from the center to the boundary of the region. If we consider the membership function, we can consider as a circular one. Here it is elliptical. Now, at the boundary it's 0, but there is a smooth transition from 1 to 0 from center to the boundary. That was the understanding for fuzzy point, and we started working from here only. Now, we started giving the definition of fuzzy point because we know in geometry point is the basic element. Once the point moves, there is a locus. If the locus is linear, then it is straight line. If it is non-linear, it could be conic section or any other undefined function. That's why for fuzzy geometry as well, we started from the point. What is fuzzy point? This is a mathematical form of a fuzzy point where membership function has been defined this way, and at the point 1 and 3, the membership value is 1, and beyond that, the grade of membership is diminishing from 1 to 0. Now, how it looks like, if it is fuzzy point, we have to define it because we want to connect to fuzzy points, then only it would be a line segment. While we started doing that, now the question arises, how to connect the points, because this is a collection of many points together. A fuzzy point is not a single point. This is a combination of points, but with different membership values. Now, if we consider 2 points together in the space, how really we can connect? Which point to be connected with what? That's why we started thinking about it. We could define, you see, if I just draw a line and we could see at the line, it is a simple fuzzy number. But in our conventional idea, fuzzy number always we define on the real line. That's why, how to say this is a fuzzy number? That's why we thought about it. If I just turn around the lines, we could see this is nothing but a combination of different fuzzy number kind of things together. Because once we can define the point as a combination of fuzzy numbers, then my job would be easy. Now, from here, we have defined a new concept, that is the same point and inverse point. I will just show you in the next. At least I could summarize here that a fuzzy point can be considered as a combination of fuzzy numbers, provided fuzzy numbers are defined in different directions, not on the real line. Now, how we can visualize it? You see there is a fuzzy point P. From there, this is a membership. The direction is the membership value. Just if I take the cross section with a plane, we could see we are getting all these numbers I just showed you. Now from here, we could say this number is a combination of many points together. Now how really we can define it? Can we say that we are taking a line which is making an angle theta with x-axis? By changing the value of theta from 0 to 2 pi or 0 to pi by 2 rather, we will get different numbers. Now from here, we thought thinking about it, and we have defined fuzzy numbers in a very nice fashion. But before to that, we have to define the fuzzy number at different directions. Because as I was saying that fuzzy number may not be on the real line always. Now this is a fuzzy number. All of you will accept this is a fuzzy number. There is no doubt about it. From 0 to 2, the membership value is from 0 to 1, and from 2 to 3, it is from 1 to 0. Now, if I just move this fuzzy, if I just do a transformation along a line x equal to y, that means the line which is making 45-degree angle with the transformation, xy is becoming uv with the angle theta, then it is coming. This value is coming here. You see, this is the transformation. And with the transformation, instead 2 is becoming, it was 2, 0, it is becoming 0.2, 0.2, and 4 is becoming this one. That's why once we could define it, Therefore, we can define the transformation of fuzzy number, rather the fuzzy number, along any line in the two-dimensional space. We have defined it in two-dimensional space, but the same idea can be extended even for three-dimension or more. Now, this is the basic thing we started. Now, this is the formal definition of fuzzy point. It has been said that fuzzy point may be viewed as a collection of fuzzy sets or fuzzy numbers as P equal to union of all P theta, and where theta is in between 0 to 5. Now, membership function of this is this one, where we have considered that LP theta is a line. I will show you graphically how it looks like. I showed you before as well. This is a line which is making theta angle with x-axis. Now, Dubat Rade, we are referring because he said in 1979, we are doing operation on fuzzy number, but we cannot. We are developing the fuzzy geometry, but we cannot deny the invention, the rules, the ideas, theorem of extension principle, because that is the basic guideline for doing any fuzzy operation or fuzzy relation. Now here in 1979, it was mentioned that this result was very much important for developing the whole geometry, because it has been said that if we consider a function phi, which is increasing function, then we can say that if the membership, there is a point x1 star, x2 star, and xn star with the value of phi, x1, x2, xn, then the operation, if we do the operation, phi operation on this point, fuzzy operation on this point, this membership value is similar to the individual. There must be an equality sign here. Now this must be equal to f1, x1 star, f2, x2 star. That is the individual membership values it has been considered. And that was the starting point, because it has been said that always do operation with increasing part with the increasing part, decreasing part with decreasing part. But you see, when we are considering the extension principle, even for a fuzzy addition, we consider that fuzzy addition considers all combinations, whatever possible. From there, we are making submin combination. But with this idea, we can reduce our load of calculation. The simple example. Here, we are trying to add two numbers, LSI fuzzy numbers. One is fuzzy 2, another one is fuzzy 6. And it is this one. Now, here you see, we want to find out what is the membership value for 8.5 at the fuzzy 8 fuzzy numbers. Now, you see, in the extension principle, what we do, we consider all the combinations which forms 8.5. For example, 2.25 plus 6.25, 8.5. 1.5 plus 7, 8.5. 1.9 plus 6. These are all 8.5. Now, from here, we are considering the mean of the individual membership values from the all combinations, and we are taking the least upper bound, that is the sub combination from the whole set. That's why you could understand, you can imagine that so many numbers we are just doing operations together. But if we just consider this theorem, it suggests that we need not to really consider all combinations together. What does it mean? It means that you see the combination 1.5 and 7. 1.5 in the left hand side of 2 and 7 is the right hand part of the next fuzzy number. This combination, if we consider, this is redundant. We need not to do. Always we will go for left hand side with the left hand side, right hand side with the right hand side, and we will do the combinations from there itself. 2.25, 6.25 is acceptable because both are in the right hand side. 1.8, 6.7 is not acceptable. And if we just find out any combination from there, and we could see that the individual membership functions, membership values are coming same. That was the understanding in the next. And from there, we started thinking about the fuzzy line segment for joining two fuzzy bonds. Now, you see there are two fuzzy points, P1 and P2. You see there are numerous applications of this fuzzy geometry. Now, recently, I have worked with Professor Laszlo Tifosi on, he is an exponent on fuzzy interpolation. Now, he has many publications on fuzzy interpolation. There we have applied the fuzzy geometry very nicely to get the interpolated, extrapolated value. Even for the inverse interpolation we have done. Now, this is one application. Other application, I could see that in the medical image, we could see the images in the medical science like a cell. The boundary of a cell is not crisply bounded. That is again a fuzzy curve. That's why there also one of the application is there. Now we will do one after another now, but let me just tell you what the basic work I did till that. Now you see, this is the joining of two numbers. Now there was an idea by Buckley and Islami. It has been said that whenever you are connecting two numbers, fuzzy points, rather not numbers, fuzzy points P1 and P2, then you consider a point A1 from that point and A2 from the next point, and you just take the crisp line between that. Therefore, you can imagine we can consider many infinite number of points here and infinite number of points here, and I can connect. I will show you what is the difficulty we are facing with this. Now, if we just connect it, one point taking from one, obviously we need to consider the membership grade. Membership values are being circled or the squared with different values, and you see, if we just connect with this within the membership values by making the membership values 10, by using the theorem I showed you in developed by Duba and Prade, you could see we can get a bunch of lines like this. And this bunch of lines will intersect each other. And as a result, what is happening, it is, though this is looking like this, but it is taking a different effect. I will show you in the next. But you see, if we just even insert another point, see here, we are losing the information of this because the fuzziness is less than these two. But always in information technology as well, we say, everywhere we say, as much as information as we can gather, we should use it with proper space. That's why losing information is not really very much encouraging. And not only that, we just connect the whole line is just taking in this shape, according to Buckley and Islami. Okay, therefore you see, beyond P3 and below to P1, it was taking a butterfly effect. It is fading outside. That means it is not forming at all a line. We know the fuzzy line could be seen as a hazy band, where at the core line there is a strong black, and once we are moving from the core to the boundary, the membership value will decrease from 1 to 0, and in image it will be the black color will fade it out from blackish to whitish. This is our general idea for hazy band. That's why we were saying that this is not the correct idea to define the fuzzy line segment because it is taking this shape. And it is any question you have? Or shall I continue? Hello? Am I audible?
Yeah, you are audible.
Okay.
Any questions from the participants?
Okay, thank you.
Okay, you can continue.
Okay. Now, if the fuzzy line takes this kind of shape, now it lacks inner conformity, because if we just want to make membership value from just to 1, instead by taking fuzziness a lot, we could see that we cannot define the line in a classical sense. That's why we consider this idea maybe we have to drop it. We started thinking about it, and we can connect to points P1 and P2 by the linear combination lambda P1 by 1 minus lambda P2. That is the line segment we know very well. That's why any point in between can be defined as with the linear combination of these 2 points. Now you see here there is a number, here there is another number. You see both the lines are making the same angle with x-axis. Here it is 0, it's making 0. Now you see, if we just connect the left hand part of this number of P1 with the left hand part of P2, then we can connect these two at different alpha level. Even right hand with right hand, then we can connect. This way, if we just change the directions for everything, for P1 and P2 for all the lines, and if we just apply the Dubai-Prade, what they developed in 1979, and that we can do very well by connecting those, we are getting a fuzzy line segment in a very nice fashion. And this is a definition. I will come to this definition later on. I will show you how it looks like. It will look like this, as I was mentioning, because left part will connect left part and the right part will connect with right part. Then there is no intersection in between. Fuzzy line will take its shape. Now I will show you the definition of it, what really we wanted to say. It has been said that if I consider P1 and P2 two continuous fuzzy points, and by taking x1, y1 in the first number and the x2, y2 in the second point, if we just connect these 2 points by considering the left hand part, that how to mathematically define the left hand part, by considering x1 star lesser than a, y1 star lesser than b, x2 star lesser than c, and y2 star lesser than d, then the left hand parts will be connected together. And if we just reverse the sign, it will be considered as the right hand part. In that way, if we just connect and we develop this theorem, and if we just do it, we could see this red will be connected with red. Now, if we just connect this green with this green, then that intersection between the lines are coming. That's why we are not encouraging this one. And from here, we have said that these red 2 color points are the same points, and this green 2 points are the inverse point, because that is the guideline for any fuzzy operation, and it is not only reducing the operations we make for the extension principle, because it is just making the half of the whole complexity, computational complexity. And not only that, very nicely we could visualize the fuzzy object in a better way. That's why we have suggested and we have said the definition of the same point as this one and the inverse point in the other way. These are the inverse points. Okay, and we said connect same with the same and inverse with the inverse. And inverse will be considered then only when we are doing the subtraction or division. Otherwise, for addition or multiplication, we will go for the combination of the same points. And this is the idea for it. And you see, with this idea, the fuzzy line segment looks like this. Okay, you see, from here, there are 2 advantages. The first advantage is that all the information of 3 given points, P1, P2, P3, we could nicely incorporate. Not only that, the next advantage is that, and if we just want to make it in the classical sense, very easily we can explain it geometrically and numerically, because we could visualize in a better way than Buckley-Islami suggested. Okay, this is Buckley-Islami's approach and this is our approach. If we could identify, our approach is totally dependent on the idea of the same point and inverse point, but Buckley-Islami suggested consider all combinations whatever possible. That is the difference between these two. And we started doing operations, and Buckley-Islami's approach, the line looks like this, but in our approach it looks like this. Now the question comes, this is a fuzzy line segment. Now if I want to make it for the whole line, how it looks like. For example, there are different points given, P1, P2, P3, P4, P5, all are with different membership values, all are taking different shapes, then how it looks like. With the same point idea, we have defined that you connect the same point this way from P1 to P5 and beyond P5, consider the information given in P5 and below to P1, consider the information given in P1. This way, we can define any fuzzy line of infinitely long. Okay, and you see at any point we could define a fuzzy number, but the fuzzy number, rather the fuzzy set of fuzzy numbers, this is being defined in a different line, which is making different angle, not the x-axis at all, as I was mentioning before. Now, once we could provide the fuzzy line, we need to tell the definition for it. We need to say the closed form for it. Now, here you see there are many works remaining to do. For example, we know any line is a combination of, any crisp line is a combination of different points. That's why in an Euclidean space, if the x is given, if I know the equation of y, I can find out the value for y. But in the fuzzy sense, we are having the equation in a fuzzy form. It could be ax plus by equal to c, or it could be y equal to mx plus c, any form. Line can take different form, 2-point form, slope intercept form, and intersect form, many form it could take. Then there is a responsibility to define all these types of fuzzy lines. That's why I will show you in the next how really we have defined the 2-point form and the other things. Okay. Now, at least we could give some idea how the fuzzy line looks like. Now, we have said the 2-point form. That means when P1 and P2 information is given, we define 2-point form, consider the line segment with the same point, and the below to P1 consider the information of P1, and beyond P2 consider the information of P2, and consider the infinite line with that fringe. When alpha cut of this is given this, and the slope can also be defined, and here we could see that the slope is not a crisp slope of that fuzzy line, certainly. This is again a fuzzy set. Therefore, once we could define the slope as a fuzzy set, now there is a remaining to do is the fuzzy trigonometry. If the slope is fuzzy, if the form is fuzzy, if the height is fuzzy, how to define tan theta? Work we have published few works on this, but there are many more works are remaining to do on this fuzzy trigonometry. But today I am concentrating more on fuzzy geometry, not trigonometry. Now this is the 2-point form of a fuzzy line. 2 points are given, and this is the equation I showed you how it looks like, and this is the shape. Now, once we are getting a fuzzy line segment, then the question comes, if 2 line segments are intersecting together, then what would be the intersecting point? How it looks like? Now, this is a closed form of a 2-point form. I will give you the answer for the previous question. But before to that, I will show you different definitions of the 2-point form, where 2 fuzzy points are given, how to define the line using these 2 points. This is the definition for this. And this is the y-intercept form. This is not 2-point form. This is y-intercept form. When 1 point is given and the slope is given to us, we can define this one. Here, y equal to mx plus c, and we know we can define c is again a fuzzy in nature here. Now, this is a point slope form. Similarly, slope intercept form, and this is looks like this. These have all defined, and the theory behind that is already developed. Now, I cannot explain it now, but I can only tell you that if the intercepts are given for to us, x by a plus y by b equal to 1. That is the equation for the crisp line intercept form. Here, instead of a, here it is given a fuzzy number. And b is also given as a fuzzy number. Therefore, the equation would be x by fuzzy a plus y by fuzzy b equal to 1. And we can connect these two points like this. And any point in between, we can find one fuzzy set. Therefore, the membership function we can use the two-main combination there as well. And here also the same idea we have done, the only thing we have done, the same point concept. And through the same point only, we have developed the whole fuzzy geometry. And it is working very fine. And with that, we could develop all the definitions of fuzzy up to the fuzzy connect section. Now, this is the intercept form. Now, the question arises, as we know in the crisp geometry, that is the conventional, I would say conventional geometry, Cartesian geometry, as we know that all these forms, that is the slope form, intercept form, that there is a connection between one can be transformed to other. X by a plus y by b equal to 1 can be transformed to y equal to mx plus c. But in fuzzy sense, is it really possible? Now, here we could prove that intercept point and the 2-point form are conversely true. One can be transformed to other. Similarly, slope intercept and the point intercept form, point slope form, they can be connected together. That means one can be conversed to other, vice versa. But all are not really we cannot convert any one of the four type to other type. This is only possible, all are same when all are equivalent when slope of all fuzzy lines are real constant. If the slopes are fuzzy, then all forms are not equivalent. And if the slope is fuzzy, you must be understanding, because if the slope is fuzzy, we are doing lot of operations there with the same points. And for every operation, uncertainty increases. Even for the subtraction, for any operation, addition, subtraction, multiplication, division, always we could see that the uncertainty increases. Therefore, if the slope is fuzzy, due to that fact, we could see that one cannot be transformed to others. But we could prove that if the slope is constant, then one can be converted to other. All the types are equivalent. Okay, this is one part of it. And we can say from here that this is a fuzzy line segment, and we can make it a fuzzy line, and anywhere we can define a fuzzy number along a fuzzy line this way. All right. Now, as I was saying that there is two fuzzy line segments. If they intersect each other, we know if in the conventional geometry, if two lines intersect, we get an intersecting point. But here, getting intersecting point is not so easy, because both the lines are having different grades of uncertainty, and finding out the intersecting point, it may happen the intersecting point will not belong to the individual fuzzy line segments. That's why there was a need to define a transformation of fuzzy points. Transformation means that is the translation, rotation, contraction, and the expansion of fuzzy points, because whenever we could see that the intersecting point is outside the individual line segment, we have to contract the fuzzy point, and with that contraction we could find out the intersecting point. Okay, And there is a theory behind it. It is not so easy to get this intersecting point at all. Now we have developed this theory, and with that we could find it out. But still here another question comes. As I showed you that every fuzzy we can get in individual line, at any point we will get a fuzzy number. Okay. Similarly, at the intersecting point also we will get two fuzzy numbers from two fuzzy lines. And connecting all fuzzy numbers together, we will get the intersecting point. But will it at all a fuzzy point? There is a question on it, and we are working on that part. There is another question is there in fuzzy geometry, that here all we have considered the membership function as a convex set. We know the fuzzy number is a convex fuzzy set, but in general, if we consider any generalized fuzzy set theory, there the fuzzy sets are not convex in nature, there the non-convexity may be there. That's why how it looks like then for two non-fuzzy points, how if we connect two non-fuzzy points, how the fuzzy line segments look like. We won't get so nice figure like circle, ellipse. The figures will be something different. Now there also we have started working on it, how to define the non-fuzzy geometry as well, because non-fuzziness, non-convex fuzzy geometry, not non-fuzzy, non-convex fuzzy geometry. You know, the non-convexity means there is not a single idea. There are different ideas of non-convexity. It can take different functions. There is no single nonlinear function defined in literature. Different nonlinear function gives different shapes of fuzzy points. That's why developing fuzzy points in a non-convex plane is not so easy. Working on that part as well. Now, in a nutshell, I can say that the fuzzy lines can be defined as a by infinitely extension of the fuzzy line segment, and a line perpendicular to the core of fuzzy line is again a fuzzy line, and fuzzy line we have considered the normalized. But you see, for the non-convex fuzzy geometry, fuzzy line may not be normalized as well. All of it normalized means the highest membership value is 1. But in non-convex geometry, the highest membership value may not be 1. Therefore, to find out the customary definition of it is a real difficult task. Now, once we could find out the linear combinations of two fuzzy points, why we are not defining the other part, that is the fuzzy triangle, fuzzy circle. Now we started doing that part. Now for circle, we know if the center is given as a fuzzy number, radius is given as a fuzzy number, then how a fuzzy circle looks like. For example, it is given that the center is at around 1 and 3 in two-dimensional space, and draw a circle of radius fuzzy h. Then there must be some construction procedure for defining the fuzzy circle here, and that procedure we have developed. You'll see, and we could see that if the fuzzy number given in the center is symmetric in nature and the radius is symmetric in nature, then fuzzy circle will be again a symmetric fuzzy circle, where at the center we will get the crisp circle, and once we will be out of the whole range here, the membership value will be from 1 to 0. All right. Now, at least it is possible to define a nonlinear function, which is a fuzzy circle. Now, if there are 3 points given, we can draw a fuzzy triangle. With the same idea, again, you see, we have only connected the same points. Here, S1, S2 are the same points. T1, T2 are the same points. But the S1, T2 are the inverse points. We never connected that. Similarly, if I consider 2 points P1 and P3, then S1 and S3 are the same points, P1 and P3 are the same points. They belong to the same membership value. Not only that, if I consider a fuzzy set at the center of P3, then S3 and P3 both are residing in the two sides of the core value. That's why both are the inverse combination. In that way, if we just connect, you could visualize how a fuzzy triangle looks like from here. Now you see, there are different examples we have done. Now, if the sides of the triangles are given around 3, around that one, and the angle is given 45 degrees, then we need to draw a fuzzy triangle. That is also possible. How to do it? Because we will find out 3 points like this. We will just get the shift the point P to Q, okay, with the length fuzzy 2√2 and which is making the angle 45 degrees. In that way, if we just define and once we will get 3 points together, we can draw fuzzy triangles by connecting the same points there as well. Now, once we could define fuzzy triangles, then the next question comes: how to define fuzzy similar triangles? When to say 2 fuzzy triangles are similar? There are also certain conditions we have developed, just like in analogy to the standard classical Euclidean geometry. The same geometry we have developed here. And you see, when 3 points are given, how to draw the fuzzy circle. You see, the points are not really points are symmetric in nature, but points are not taking the same shape. That means the level of uncertainty for different points A1, A2, A3, these are not same. One it is circle and somewhere it is ellipse. How to connect these? But if we use the same point concept here again, therefore finding out the fuzzy numbers along the lines, and you see all the lines once we are considering, it must be considered the line which is making the same angle theta for all 3 numbers. Then only we can define the same point, otherwise not. Therefore, you see this line is making angle theta, L2 theta is 2 theta, L3 theta is 3 theta, all are making the angle theta with the x-axis, and we can define fuzzy number along this line, and we will just connect left with the left, right with the right, and once we are doing so, we are getting this fuzzy circle. Here you could see the fuzzy circle is not symmetric. Uncertainty is not spread uniformly over the whole circle because of the nature of the points given to us. P1 is elliptical. The major axis and the minor axis ratio is not same as P2, and P3 is a circular. Therefore, circle is looking differently for this case. Notice the same like previous. We have defined fuzzy parabola as well, like this, where 5 points are given to us. Fuzzy points are given to us. We have developed the equation to develop for this fuzzy parabola. And we have defined the lattice rectum, etc. That is a case the geometry in objective optimization problem. Along the paragraph front, which I showed you text, but still many works are remaining to do. For example, if I just give a simple example of a innate, you try to visualize if it is fuzzy in nature, then the bounded region, the boundary of the bounded region would be again a fuzzy in nature. Therefore, if the objective function for maximization, minimization, objective function moves freely within the space, then if it touches the boundary of the feasible region, then only we get the optimal solution. But here, touching and will form a fuzzy point. And we know always at the extreme points, we get the optimal solution for a linear programming problem. Therefore, identifying the fuzzy extreme point is not so easy at all. Now, that also could be the starting point for fuzzy optimization. We have done a little on that. We are doing more on it. And hopefully there would be more applications other than hardcore mathematics. Anybody can do it in medical imaging and other cases, but you see the third reference we have done in interpolation. There are few more references on interpolation as well. We have done it, and with this I would like to complete my lecture, and thank you for listening. If you have any question, I'm hope you can
Thank you so much. Thank you so much, ma'am, for your nice and interesting talk. So now I would request audience, if you have any questions, so you can ask directly to our speaker.
Hello, ma'am. Good evening, ma'am. While drawing fuzzy triangle, do we need to consider all the vertices of the triangle the same type of fuzzy number? Can we use different types of fuzzy numbers or fuzzy membership?
That I was mentioning to you. If you consider same type of fuzzy numbers, what will happen? Your fuzzy triangle would be symmetric. All the sides, I should say the spread of the uncertainty will be similar. Okay, but in general, in reality, it cannot happen. That's why better not to take in general the fuzzy numbers with similar signs. Better you take different kinds of fuzzy uncertainties there.
Yeah, thank you, ma'am. Thank you.
Thanks.
One of the questions from an participant from the live session: can we apply the idea on fuzzy line for solving systems of linear equations?
Yeah. Linear equation like x plus by equal to c. First of all, you need to see if a is a fuzzy number, b is a fuzzy number, c is a fuzzy number, then how it looks like. Okay, that you have to start working from that only. We have done some work on that, and hopefully it will come to the journal very soon. How it looks like. Simple work, x plus by equal to c, y equal to mx plus c, how it looks like. And few works we will get in my basic book published already in Stranger. You will get the basic idea there, how it looks like.
Okay. Any other questions from the audience? If not, I have one question. So,
yes,
as I understand, the fuzzy geometry is like visualizing the fuzzy point or different shapes in two-dimensional space in the three-dimensional space, right? So it's a very general question. How this fuzzy geometry is like more have a good property or more different than the classical geometry? Like, what is the advantage of using fuzzy geometry for solving multi-criteria decision making and all these things?
Now, we are using fuzziness depending on the information given to us. Why we are using fuzzy? If the information is not precise to us, then we are just substituting any numeral with a fuzzy numeral. That is the basic idea of using fuzzy. We are not forcefully we are using fuzzy number anywhere. Okay? We are gathering information. Fuzzy set is being formed from the reality only. That's why you are having one channel. For example, I can give you one idea that I was discussing with one person. He's from now in the mobile network. You are moving with a mobile in a certain with a locus. But if you see it from the satellite or UAV, your position is not visible as a very crisp locus. Always you will see the locus will be fuzzy in nature. All right.
Yeah.
There, why don't we apply fuzzy? If we make it crisp, that means we are doing certain approximation. Approximation means losing information. There, if we use the fuzzy geometry, hopefully it will give you the better result. Losing information far from the reality. Gather more information as you can. That is the basic idea. That's why wherever crisp geometry is not applicable, why you are forcing it to apply it? Go for the fuzzy geometry and do it.
Yeah.
But lot many theory are yet to be developed. There are many works are remaining to do. This is not really I cannot do in my life. Because you understand this is a parallel theory is going like with classical geometry. Hopefully in future people will take interest on that and do some work. But I am my specialization is optimization.
Yeah. Okay. Yeah. Thank you so much, ma'am, for your interesting talk. And you joined us in a short notice, and you took the time from your busy schedule and give me a nice presentation.
To you for giving me opportunity for this. Really, I'm thankful to all of you who are listening for 1 hour to me. Thank you.
Yeah, glad, ma'am, that you joined us.
I'm also very glad to meet you.
Okay, thank you so much, ma'am.
Thank you. Had a nice time with you. Do you have any other plan today? Any other lecture do you have?
Sorry, ma'am, can you ask once because your voice is not audible?
Have any other lecture today?
Yeah, we have one lecture from Samrat Gupta. He will be discussing about rough set application in complex network systems. And there will be another talk from Professor Sostak, and he will be discussing about the fuzzy mathematical morphology.
Oh, so nice. Okay.
Okay. Thank you so much, ma'am. So dear participants, we will be having the next two lecture. So one from our next speaker is Samrat Gupta, and the last lecture will be Professor Sostak. So as you see that yesterday we had only one lecture, so we received the study lecture in the today's session at 4:30 according to the Indian time. So now I would like to request Dr. Rishikesh Datta Tiwari to give the brief introduction about our next speaker. So Rishikesh, please.
So thank you, Dr. Anand, and good afternoon to all of you. Now I would like to welcome our next speaker, that is Dr. Samrat Gupta. Dr. Samrat is an assistant professor at Indian Institute of Management, Ahmedabad. He received his doctoral degree from Indian Institute of Management, Lucknow. His research interests are in the area of information systems and management, with a focus on the soft computing complex networks and online platforms. One of his projects on investigating polarization in social media has received funding from the MHRD under a competitive granting scheme named as Spark. His research has received several awards from the reputed organizations around the world, such as IDRBT, Hyderabad, and Complex Engineering System Institute, University of Chile. He also won the highly commended paper award at third international conference on the business analytics and intelligence held at IIM Bangalore. So welcome, sir, to deliver his talk. So once again, I invite Dr. Samrat to deliver his talk. Over to you, sir.
Samrat, can you please unmute yourself?
Okay. Yeah. So, am I audible now?
Yeah, yes, sir.
Yeah. So, thanks, Dr. Rishikesh, for such a nice introduction, and thanks everyone, Anand, Mahesh, Rishikesh, and Ashok Kumarji, for providing me this opportunity to speak here about my research work. Uh, so, I'll share my presentation. Is it visible to everyone?
Yes, sir. So make you full screen. Okay, now perfect, sir.
Okay, fine. So, yeah. So, I'm really glad that this kind of workshop, online workshop, is being held, and various participants, including the PhD students and all, can take benefit of it in the area of fuzzy and rough set theory. So, my work is basically more towards the application of rough set theory, and in the basically in the domain of networks. And we see a lot of networks these days in typically in every domain, whether it be engineering or business or society, any domain you name it, and we can model that system or a domain in the form of a network. So this work has basically a lot of applications, and I've been doing this work for last 5 years. I started this project as a PhD student in 2015, and I graduated with some publications, and then I'm still doing one of the projects. All is like I'm continuing on this project and working on the same rough set theory and complex networks, uh, so as to advance the algorithmic community detection phenomena in complex network. Okay, so that's about it. And at the outset, I would just like to show you some of the publications that have come through this work. So these are the three publications which I have published till now. One is in information sciences, another one in data and knowledge engineering, and the third one in decision support systems. And this one is close to like we have submitted it, and this one is again under review in a journal, and there are a couple of more publications that we are working on right now, which are particularly related to this work. Okay, so now let me start with the straight away with the motivation of this work. What is the core business problem? I hope I'm audible to everyone, and my voice is clear, or is there any problem?
So voice is clear, sir.
Okay, okay, fine, good. So let me start with the basically the example of what I'm going to talk about. I'm going to talk about complex networks and the communities in networks. So we all know that we are on Facebook and Twitter and all that, and we all know that there are communities in social networks. Social network, each one of us know. We are so much familiar with social networks today that we are all are aware of social networks, and the presence of community in social network is very clear to us. For example, in Facebook, we have groups, but those groups are explicit groups, right? So we have groups pages for each of the groups, and we join or unjoin that group, but they are kind of explicit. We know that this is a particular group related to, say, fuzzy set theory or data mining or whatever. So, but in real life networks, the groups or communities are not always explicit. They can be implicit also, and then it becomes a challenge to detect or identify these implicit communities or groups in networks. And not only social networks. Social network was just for an example. As I said, that these networks has basically they have permeated each and every domain that we talk about today, whether it be sociology, economics, finance, engineering, business. Every system can be basically modeled as a network, and then there is a presence of communities in these networks. Okay, so this is one of the examples that I would try to motivate the study with. So suppose there is a vendor. Uh, are there some questions or something like that?
No,
Are
sir,
there
you
some?
can continue. No, sir,
Okay.
you can continue. Question will be taken in the last of the event.
Okay, fine. So, suppose there is a mobile phone vendor such as Vodafone, and it has some customers. Okay, like this, there are a lot of customers, and here the size of the node basically denotes the revenue that a particular customer is creating for a company such as Vodafone. Okay, for example, this is a larger node, so this means that this person is creating a lot of revenue for Vodafone as compared to the smaller customer, say this one. Okay, so suppose there is this customer which is a very small revenue generator for Vodafone, doesn't generate much of the revenue, but still she is a customer of Vodafone, and suppose she basically calls Vodafone customer care one day that she is not getting a good service from Vodafone and all that. She starts complaining, and therefore she is going to drop the Vodafone network. Okay, so how much effort should Vodafone put in retaining her? How much efforts, or basically how much, what should be the churn ratio of Vodafone such that it should decide whether it should retain this customer Geeta, let her call as Geeta, or let her drop the network. So it will obviously depend on the revenue that this customer is creating for Vodafone, right? So traditionally, since she is a low value customer, she doesn't generate much revenue for Vodafone. Vodafone may let her go, drop the network. It's okay. Vodafone has a lot of high value customers, so just focus on these high value customers like these ones, and let Geeta drop the network because she is not willing to continue with the network, and maybe she wants some extra incentives or something like that. But see, suppose Vodafone tries to drop Geeta because she is not a very high value generator, then what may happen? Geeta drops the network, then subsequently, because Geeta was embedded in a group of other users which were also high value customers. This was a community of users which was not very explicit in the beginning. Okay, but there can be such groups which exist in the mobile network of consumers. So once Geeta dropped the network, then other high value customers may also dropping the network. For example, this one, because maybe he is a friend of Geeta or so on, and then maybe other customers also start dropping the network because Geeta has dropped the network. So what has happened is basically a low value customer has dropped the network, but this low value customer has led others to drop the network also, and therefore Vodafone was in the beginning not able to decide whether Geeta is a high value customer or a low value customer. So it let Geeta drop the network, but subsequently there was a large difference in the revenues that happened for Vodafone because of Geeta. So if we are able to detect these kind of communities of users, then it is possible to basically see how much revenue a particular customer like Geeta influences, total revenue influenced by Geeta rather than the revenue generated by Geeta. Okay, so this Vodafone just thought about the revenue generated by Geeta, not about the revenue influenced by Geeta. So this basically gives rise to a new problem, a new way of looking at the problem of retaining the customers. Okay, and it is possible only if we are able to detect these kind of communities, what kind of groups exist, what kind of who is calling whom, and how close they are embedded with each other. So this problem of community detection is really very important, and this is one of the examples in the mobile phone network. Similarly, let me talk about this another example. So for example, suppose there are banks in a financial system, in a financial economic system, there are banks, and these banks have given loans to various firms. Generally, banks do give loans to firms. Okay, that is how our economy functions. And then these consumers basically use the services and products of these firms. Okay, so suppose these lines basically denote the credits or the loans given by this bank to this firm and so on. Okay, so suppose this particular bank, this particular firm becomes bankrupt. It has taken loan from these banks and it becomes bankrupt, and therefore it is not able to pay its loan. Okay, the company is not able to pay back its loan. So what will happen is this company won't be able to pay back its loan to B2 from which it has borrowed the loan, and so B2 will not be able to in turn, because it was not able to get back the money. B2 would be reluctant, or maybe may face difficulties in lending money to other companies like F2 and F3. So that is how there will be a choke. The entire financial system will be choked because of the bankruptcy of a single bank. Okay, and therefore it is dependent to find out like which banks are in a single group, in a community, as with reference to the credit relationships. Which banks have given loan to the similar companies or same companies, and how are they linked within a community? Because if you talk about a community, if there is a bank in a particular community and it receives a shock, a particular company denies to pay back the loan, then all the banks in that community will be suffered, because then other companies will not be able to receive the loan from bank B2, then they will go to bank B3 to receive that loan, and there will be a lot of pressure on B3 or B4. So all the companies which are in the same community will face a lot of pressure because a particular bank has become bankrupt in that particular community. So again, it is important to detect the communities of banks and firms in these kind of economic and financial networks. And basically, I am talking about these examples because we have used rough set theory to detect the communities, and we are still advancing the use of rough set theory and fuzzy set theory so as to detect communities in weighted networks and unweighted networks. So these are some of the examples just to motivate the problem. Now, let's make it more generic. Like I just talk about two kind of networks, two kind of systems: a mobile phone system where consumers are calling each other, and the another one was financial system where banks are giving loans to companies. Okay, now there can be various kind of such systems, and these systems are collectively referred to as something called as complex systems. Okay, we can have society. Society is also an example of complex system. Financial system of banks is also an example of complex system. We talk about mobile phone vendors and so on. All these are examples of complex systems, and these are basically made up of different entities. Okay, so for example, when humans basically interact among themselves, they lead to of complex systems such as society, cities, populations, where these are all examples of complex systems. Okay, society, we know that we on Facebook we call them we model them as social networks. Okay, but similarly we can model cities and population also as networks. Similarly, when we have technological entities like laptops, routers, okay, and so on, then these kind of systems lead to something called as internet. Okay, internet and world wide web is also an example of complex system, and all these have communities among themselves, a community or a group of routers and so on. Okay, another example is, yeah, so when I was talking about financial entities like markets, organizations, banking systems, political systems, all these are examples of complex systems, and we can model them using rough set theory, networks, and so on. So I'm going to show you that in a while. Similarly, our body, human body, consists of various kind of cells and neurons. All these various kind of complex functions take place in our body, and these are also termed as complex systems. And same principle, same mathematical principle of social networks, of which we are very familiar today. We are very familiar with social networks today, but not maybe with other kind of networks like banking networks, political networks, and brain neuronal network in body, cellular network in our body. So all these are examples of complex network, and they follow, all of them follow the similar mathematical properties. Okay, like in ocean ecosystems, we have ecosystems like coral reefs and so on. So all these have similar mathematical properties and can be modeled using rough set theory and networks. That's the point here. So here are some like characteristics of complex system. As you saw, complex system is a system with a large number of building blocks or agents. Like we saw, these building blocks can be humans or technological agents. Okay, or maybe cells in human body, and they interact with each other within their environment. So all these kind of examples that I showed you, cultural, economic, sociological, technological, ecological, are all examples of complex systems, and they have some characteristics. Community, existence of communities is also one of these characteristics, one of the characteristics where communities evolve. They keep on evolving, people keep on becoming friends with each other, and sometimes they defriend each other. So these kind of dynamics keep on going on, and that is why communities keep on evolving in a network, and we detect the communities using rough set theory. Okay, so now network, these kind of systems like complex systems can be modeled using various kind of mathematical approaches. For example, some people have worked in the area of mean field theory. Some people have used nonlinear dynamics to model complex systems. Some people have used statistical physics to model complex systems. Okay. Similarly, networks is also one of the paradigm to model these complex systems. Okay, and it is really very relevant and emerging paradigm, particularly in the domain of engineering and business today. Because we see a lot of data being generated in the form of networks, and we have online platforms. Okay, we have so many online platforms, and all these platforms are doing nothing but collecting the network data of interaction between the consumers, okay, and the organizers of the platforms. So when we talk about social networks such as Facebook, again, you see that it is a network and there are communities in this. Similarly, there can be organizational networks like industries. Various kind of industries are there, and the board of these industries are sitting on each one or the another industry. So there is interaction between the board of governors of the industry. Similarly, there is co-authorship network. Scientists basically collaborate among themselves to publish research papers. So I collaborate with someone, he collaborates with someone, and so co-authorship networks are also formed in such a way. And DVLP, if you talk about DVLP, it is based on the same principle of co-authorship networks. I talked about neural network, citation network. I am citing someone's research paper, someone else is citing my research paper, and so on. So these citation networks also take a form, or they are also organized according to the discipline. For example, if I'm doing a particular kind of research, I will cite the research within the same discipline. Okay, so these disciplines in citation networks are also organized as communities. And so on. There are various examples like protein, these are more from the biological domain, and basically biological informatics domain, where people are modeling human body as mathematical networks and trying to use the mathematical principles to mine the patterns in biological cells and so on. Okay, so typically a network can be represented in the form of a graph G, which consists of vertices, or we also call them as nodes. Mathematically, we denote by this symbol V, vertices, and edges. Okay, so edges basically connect the vertices of a network, and they denote the relationship between the different kind of vertices. For example, you see these images here. This is a social network. In brain, there are cells, and they are connected by various linkages. And books network, which book is sold with which book on Amazon. Suppose you talk about a website called as Amazon, then someone might be interested in that, in forming a recommender system. For example, this book is sold with this one, this book is sold with this one. So this is a network of books on a typical website like Amazon, and so on. So these are some of the examples. And now, as I told you, there are properties of these networks. So existence of communities is also one of the important properties of these networks. Okay. For example, these networks are organized, the nodes or vertices in a network are organized into clusters or communities or modules. These are known by different names depending on the research discipline. Some people call them as modules, some call them as clusters, simply as clusters, and some people who are from sociological background mostly call them as communities. So community is a general term that has become more popular in the context of complex network. Okay, so community structure. You see here that these nodes are grouped together. They are linked with each other. These nodes are linked with each other. So this is a disjoint community structure. And what is a community? Community is basically a statistical measure of connectedness in networks. And communities identified through algorithms have a significant real world meaning. Okay, so it's not that all these communities are always explicit. Sometimes these communities are implicit. Okay, so we need to detect the implicit communities using algorithms and techniques such as rough set, fuzzy set theory, and so on. So I've already given you the examples of communities in affiliation networks, co-authorship networks, and scientific citation network, and so on. Important thing here is to understand that these communities need not be disjoint. Like here, they are disjoint. A node is a part of only one community. Okay, but these communities can also be overlapping, where you can see in the diagram below that a single node is a part of 1, 2, and 3, all the 3 communities. Okay, so they can be overlapping communities, and they can be another way is they can be nested communities as well. For example, one community is nested inside another. For example, let's talk about this example. This is a network of people, like people who are going to school and colleges. Okay, and the below the community in the lower community, which is in purple color, is a community of people who are in the same college. They basically go to same college, and that is why they have friends with each other. And this is a community of people going to same college. The above one is a community, is a larger community of people going to same school. Okay, but this contains several nested communities. For example, people who are going to same school and study in the same class are basically linked closely to each other, as compared to another community where they are going to same school and live in the same location. Okay, and some people basically there are houses. Sometime in school there are houses or groups, like different kind of houses for organizing competitions and all. So this is the small community where people are in the same house. So and they go to the same school. So you can see that this larger community of a school is organized into several nested communities. So it is also important to detect the nested communities and the overlapping communities that I talked about. These overlapping communities and nested communities. Now, traditionally, disjoint communities have been detected by various algorithms. Various algorithms based on various mathematical techniques. But detection of overlapping communities and these nested communities is very important, due to which soft computing comes into play, and it's really very helpful in detecting these soft, you call them as soft clusters or soft communities or overlapping communities in context of complex networks and nested communities. Okay, and then finally there can be some outliers also in a network. For example, some people don't like to remain isolated, right? They don't want to talk to others and so on. So a good community detection approach should also be able to detect outliers in a network as well as the soft boundaries. Okay, so that is why we use rough set theory in order to model this problem and detect communities satisfying all these criteria in complex networks. Now, let's so this is the mathematical definition. I have tried to give you an intuition behind the complex network, complex systems, and the existence of communities. That is what I was trying to tell you till now. Now, this is the mathematical definition of the problem that we are referring to. So if there is a graph or a network that we denote by G, consisting of V vertices and E edges, okay, then the objective of community detection is to discover a set of subgroups of nodes, such that nodes within the same subgroup are highly connected with respect to each other and represent the real community structure existing in the network. Like we saw in the images, the nodes within the same subgroup are highly connected to each other as compared to another subgroup. Okay, so therefore, if M communities are identified in a network, we denote these communities by C1 to Cm. Okay, and it represents a set of communities existing in V. Okay, in VNet, in the network, there is some typo here. There is a set of communities existing in the network. Okay, so you can see this. So if this is a network, there are various communities in this. This is the first community. It is the second community, and this community consists of nested community as well. Okay, and these are two overlapping communities, the orange one and the green one. So a good community detection approach should be able to detect all these kind of nested and overlapping communities if we want to detect communities in a network. Okay, so it's not that the community will always be disjoint like this one. It can be disjoint, it can be overlapping, and it can be nested. So that is the mathematical definition or the mathematical problem definition of the problem that we are going to talk about. Now, we have basically modeled and basically we use the rough set theory to detect communities in complex networks. Okay, so as previous speakers might have basically mentioned during their talks, like rough set theory was introduced by Pollock in 1982, and it provides concepts such as lower and upper approximations, boundary region, belief function, and reduction to find hidden patterns in data. In our work, we use lower approximation and upper approximation here. Okay, we basically use upper approximation to detect communities in networks, and we also use the concept of something called as equivalence relation. That what is the relation between the entities of a system that we are talking about. Of in terms of rough set theory, you call it as an information system. Okay, in terms of complex network, we are calling it as a complex network or a complex system. So basically, within the entities, there will be some kind of equivalence due to which we'll say that these two entities are similar or dissimilar. So first step is to derive the equivalence relation between the nodes of a network. Okay, so then this equivalent relation becomes very important concept in rough set theory. So what is the equivalence relation in case of networks? That we'll see now. And this equivalence relation has been like generalized from in various ways. In our case, we have generalized equivalence relation to links. We say that two nodes are similar, or basically they form a granule. I'll talk about granule also whenever they are connected by a link. Okay, so in our case, a link is an equivalence relation, and we use this equivalence relation to form a granule. Granule is basically a set of nodes or a set of identities, initial set of identities, which we call as similar, that they are similar to each other to form the clump of objects. Okay, drawn together by indistinguishability, similarity, or proximity. So in our case, links or edges that I talked about basically denote this indistinguishability, similarity, or proximity. Okay. I already told you about lower and upper approximation. We use this concept of lower and upper approximation to model the network. Okay, I hope all of you know that what lower approximation is and what upper approximation is. There are basically three things: lower approximation, upper approximation, and boundary region, which I'll try to show you through this diagram. So this is the universe of discourse, entire universe of discourse, and these are the objects denoted by the squares, and this is the set under consideration, the area under consideration. So if you talk about this particular boundary, okay, this particular line, so all the squares or objects which are definitely inside this refer to the lower approximation. These gray colored cells are lower approximation, and which lie on the boundary are basically, this is the boundary region. This particular thing in squares that you see on the boundary between the gray cells and the bold line are the boundary region, and the union of lower approximation and boundary region will form the upper approximation. And this can be represented through these equations. However, it is easier to understand it through these images, right? This is the lower approximation, this is the boundary region, and this entire thing, including the lower approximation and boundary region, is the upper approximation. So now, there have been several methods for community detection in complex networks. For example, age betweenness, and so these are not based on soft computing paradigms. Okay, these are like very old methods proposed in 2004, a decade ago. Okay, and these are mostly they mostly detect disjoint communities. I told you what disjoint community is. Like in disjoint community, it is only possible to assign one node to one community. But what if that node is a part of multiple communities? Then it won't be possible to detect it using these older methods, which are based on, you call it hard computing or traditional methods. Okay. Now, due to this, these soft computing approaches have basically, there's a lot of research which is taking place based on soft computing approaches. For example, fuzzy clustering algorithms have been proposed, then genetic algorithms have been proposed. These two are genetic algorithms, and these are quite recent, based on ant colony, differential evolution, and so on. So, however, there is a lack of, when we started this work in 2015, there was a significant lack of methods which use the principles of rough set theory, like I talked about equivalence relation and upper approximation. Okay, so this, when we read the literature of soft computing and complex networks, so it motivated us to basically start this work and form the granules, equivalence relation in complex network, and detect the community. So we basically interpreted a network as consisting of two kinds of entities. The first set of identity is nodes. We have nodes and we have links, and they form a network. So now there can be two possibilities of modeling the network. Either I consider my identities as nodes, okay, and take the help of these links as equivalence relationships. Okay, so if I consider nodes as the entities, then links will be the equivalence, will help me in forming the equivalence relations, and then I'll model the granules and upper approximation and detect the communities. And the other possibility is to consider links as the entities. If I consider links as the entities in my network, then these nodes can also help me in forming the equivalence relations. So these are two kinds of interpretations of a network. You consider node as entities and links as equivalence relations, and links as entities and nodes as equivalence relations. So these are two separate kind of notions for modeling a network using rough set theory, and that is what we do. I'll show you the first case. So this is a typical example of a social network, just a small snippet of a social network where we first form our measure. We have to always form a similarity measure to do some clustering. So let me check if there is something. Okay. Some questions?
So we'll take the question at the end of the.
Okay. I thought I thought some people are pinging, are basically doing some
Maybe
chat.
some of them are muted there.
Okay, fine. So now these are the networks, these are the nodes, and we use the similarity between the nodes by taking the common friends or common links between the different nodes. For example, here if you talk about these two, Jack and Scott. Okay, so Jack has these common friends, John, Amy, and Rob with Scott. Scott also has these three friends, and Jack also has these three friends. So generally, the measures of similarity consider only the commonality of friends between the two people. However, using this notion of generalized notion of rough set theory, we can also consider the differences of friendships. For example, Jack has so many friends, Anna, Peter, and so on, including these. And Scott has James and Alice also as friends. So what is the difference in the friendship? There is some similarity that you can see through this highlighted region, but there is also a difference. There is also a difference of friendships. So a true measure of similarity between Jack and Scott, which will enable us to do rough clustering on this, should be made up of similarity as well as the differences, between the friendships. So that is what we make use of, and I'll tell you that now. So first of all, we define a node neighborhood subset. I told you that the first algorithm that we come up with is called as ROCONA, okay, which denotes rough connectedness algorithm. ROCONA means rough connectedness algorithm, and the first definition in ROCONA is that of node neighborhood subset. For example, if this is these are the nodes, so what will be the node neighborhood subset of node 1? It will be all the nodes that are linked with this node 1 through a link. So here this link is the equivalence relation. So 2, 3, 4, 5, 6 will consist of you can call it as a granule or node neighborhood subset. Okay, in terms of rough set theory, it will be called as granule. Okay, so this is a granule in terms of rough set theory, and a node neighborhood subset in terms of complex network approach. So now coming to the other part, using these node neighborhood subsets, we define similarity measure which is called as relative connectedness. I was talking about it in the previous slide. So this relative connectedness basically takes into consideration the similarity, that is the commonality of friends. Here we are talking about intersection. The people that particular node SVI is linked to and another node SVJ is linked to. S here denotes the node neighborhood subset. We are talking about nodes VI and VJ. Okay. So what is the commonality or similarity between the friendships or the linkages of these two nodes upon the differences? This is the set difference. This is the difference of friendships, the difference of sets of the SVI set and SVJ set. Okay, and we take the minimum of this so as to keep it so as to basically keep it mathematically computable. Otherwise, it won't be give us the desired results. Okay, so this is the another which is very important definition of relative connectedness. And the motivation behind this is again rough set theory, because the measure has to satisfy certain properties. Similarity measure in terms of rough set theory should satisfy some properties, and which I have written in the research paper. You can refer to the research paper for those properties. There are 4 properties, and this measure basically satisfies all those properties. Okay, and it is based on the concept of relative connectedness, and it will lead to a formation of metrics. I'll show you what kind of metrics it will lead to, and then you can use this matrix iteratively. You can use it iteratively to detect communities. Okay, so for example, let me show you an example by computing the relative connectedness here. So this thing SVI, if we talk about V1, so it talks about 2, 5, 6, and 7. 2, 5, 6. 1 is tied to node 2, 5, 6, and 7. So the granule or the node neighborhood subset of SV1 will consist of this. Similarly, SV2, if you talk about V2, it will consist of 3, 6, and 1. 1, 3, or 6. Okay. And now if I take the difference of these two, SV1 minus SV2, it will be 2, 5, 7, because 6 is common. And if I take the difference of V2 minus V1, it will be 1 and 3. So that is how I compute the relative connectedness. This is the relative connectedness between V1 and V2. Okay, and similarly, this is another example of V4 and V9. So we compute the relative connectedness between each pair of nodes using this formulation. We compute the relative connectedness between each pair of nodes using this formulation, and it leads to a matrix of this kind. It leads to formation of matrix of this kind, where you see that there are 20 nodes in the network. So for each pair of nodes, there is a relative connectedness between the nodes. These are the node IDs. Okay. And once we get this matrix, let me show you this thing. So in the research paper itself. So this is the initial relative connectedness matrix, and we do it iteratively. So once we obtain these values, you can see these values here, and we take a threshold. We define a threshold. Okay, and that threshold will come through sensitivity analysis. You will have to do some kind of sensitivity analysis to define a threshold, and we constrain these upper approximation. Now this is the upper approximation. Okay, this was the granule, this was the upper approximation, and we are constraining this upper approximation using a threshold. So it will lead to this kind of constrained connectedness upper approximation. Now this is the constrained version of this. Okay, again we will do the same kind of matrix formulation based on the same relative connectedness. Some of the nodes will be converged, and again we will form the second connectedness upper approximation. Keep on constraining it till all the nodes, all the subsets are converged. So after some point of time, all these after some iterations, all these nodes or all these sets will be converged, and we will not be like, it would not be useful to basically carry on the computations further, because the convergence has taken place, and now it will be the repetition if you do it again. Okay, so this kind of iterative process by forming the matrix and then constraining it again and again can basically lead to the detection of communities. I can show you how. So this was the entire process of detection of communities. We did experiments on different networks, social networks, communication networks, citation network, and so on. Okay, this is the process of initialization, node neighborhood subset computations, and first connectedness upper approximation, relative connectedness computation, and little bit of fine tuning it will also require. So then all kind of communities are detected, disjoint, nested, overlapping, and accuracy of the detected communities is also high. And then we visualize it. I'll show you the visualizations next, how we visualize it, and this would be more clear to you. So these are the networks, 14 networks in the first paper that we use for the experiments. You can see that these are from different domains. Okay, and there are groups are ground truth of these networks is also given to you, like the Krate network has two communities or two groups, and so on. So, and some of them are not, the ground truth is not known. For them, we will have to use the metric. There are various metrics for deciding whether a community detection is accurate or not. Okay, so these networks we did, and so for example, this is the visualization of the first network, which is a high school network. Here, these colored nodes are the ground truth. The colors denote the ground truth, the original communities in the network. So this is a network of people who are studying, students who are studying in a high school somewhere in America. Okay, and they are organized into communities according to these colors. For example, these green nodes study in 11th class. Okay, these pink nodes they study in 7th class, and so on. These nodes, light green nodes study in 9th class, and so on. However, you see that in 9th class there are further two small communities. So the people who collected this data, they showed that there were two groups of people in 9th class. One was of blacks, ethnic basically they were separated by their ethnicity. Okay, blacks and whites. So that is why these communities were formed, and our algorithm is also able to detect the nested communities in this case. These blue lines basically denote the community detection results using Rocona. Okay, so you can see that there are some misclassification. For example, this node has been detected with this community; it should have been detected with this one. Here, there are some misclassification, but the accuracy in terms of NMI, which is called as normalized mutual index, is 0.871. The maximum value can be 1. Okay, so in terms of NMI, Rocona has very high accuracy. Similarly, these are another example. This is a network of books, political books, people buying books based on their inclination. Some people in America are conservative, some are liberals, and some are centrist. So you can see that these communities are again organized into according to their political inclination. Okay, so there are other examples as well. For example, this is a network of collaboration network of scientists at Santa Fe Institute in America. Okay, so you will see that these people basically they work in statistical physics domain, mathematical ecology. Red people denote the people who are working in mathematical ecology, and yellow nodes denote the people working in RNA domain, and so on. So the algorithm Rocona is able to detect these communities, which are quite accurate as compared to the ground truth of these networks. This is again a protein-protein interaction network. So again, you can see here there is no ground truth. We don't have the ground truth of this network, but the colors denote the communities detected by Rocona. And in this case, we have used a measure or a metric to determine how accurate this community detection is. So these are the quantified results in terms of modularity. In terms of modularity, a measure to detect community. So you can see that in case of Rocona, the modularity is higher for JAS network as compared to the other traditional algorithms. Similarly, in case of email network, it is also higher. In case of another network, which is a power grid network, it is little lower than FastQ, but again second highest. This is the second highest value of Rocona. So overall, if you see, Rocona is able to perform quite well in terms of community detection, both in case when we compare the results with ground truth as well as with the metrics like modularity and other kind of metrics. Okay, now I was talking about two approaches. The first approach was about the nodes, considering nodes as the entities. Then I talked about the second approach, which is about considering the links as entities. Okay, in the second approach, the second paper that we worked on was about considering the links of a network as entities, and then taking the nodes as equivalence relationships. Okay, so I'll show you through a diagram how we model this. So linked neighborhood subset, again this is the mathematical definition which corresponds to the node neighborhood subset. Okay, I'll show you how. So suppose this is a network, this is a TOI network. So I'm trying to explain you this mathematical definition using this diagram. So if I perform the link centric granulation of this, if I talk about this link which basically connects the nodes 4 and 23. Okay, this red link 4 and 23. So all the links which are tied with node 23 and with node 4 will form a granule. Okay, so all these links will also have their IDs. Okay, so these links will form the granule. Similarly, if I talk about this link which ties the nodes 10 and 13, then all the links which are linked with node 13 and node 10 will form a link granule. Okay, so that is how we use the concept of link centric granulation. Earlier we did node centric granulation. Here we are doing link centric granulation to detect communities. And again we use these granules that I showed you earlier. These granules we call them as link neighborhood subsets. Okay, and form a similarity measure for links based on the same principle of in the numerator is the intersection and denominator is the difference of link neighborhood subsets. So this corresponds to the same. You can draw an analogy between the node centric detection and link centric detection. Okay, so but the only difference is that these sets are the sets of links. These subsets are the subsets of links, and there in Rocona the subsets were the subsets of nodes. Okay, but conceptually it is very similar, and in this case we use these kind of networks which are from different domains to perform our experiments. Okay, there are a few other networks which were not there in the previous case. For example, Facebook was not there. Okay, and this experiment also, like the human skull of brain, the human skull, which is a biological network, consists of bones which are tied to each other using links. These links in biological terms are called as cartilages. Okay, I'll show you this network. So this is a network of bones and cartilages between these bones. So these links are the cartilages and these are the bones. Okay, so again it is also a complex network, and there are some, like there are communities in this network corresponding to the facial part of the skull, and the left ear part of the skull, right ear part of the skull, cranial complex and cervical complex. So all these complex are nothing but the communities in terms of like people in the biological domain call them as complexes. Okay, sociologists call them as communities. Okay, so these colors denote the communities or the complexes, and these complexes are basically made up of these bones and cartilages, and it is possible to detect these complexes or communities using community detection algorithm. So this was the part of our LeomCom experiment, which was not there in Rocona. Okay, it was very interesting data set. So we performed an experiment on this, and we found that the nodes were detected quite accurately in this case. For example, this was the facial complex, as I showed you. Okay, the part corresponding to the blue region, and this was the cranial complex, the second part. This is the cervical complex that you see here. All these bones are a part of cervical, and left ear complex and right ossicle means basically this corresponds to your left ear and right ear. Okay, so these bones are a part of your left ear and right ear. So now with the help of this, we are able to detect the various complexes in our body, and scientists scientists can use these complexes to determine that how a disease will, suppose there is a disease which starts with your cervical region, then these community structures can be used to decide how this disease will progress further, whether it will go to your cranial complex or facial complex or whatever. So these kind of community structures can also be used in this kind of medical domain so as to determine how a disease will evolve, okay, or how a particular problem in your body will evolve and affect other parts of the body. Again, this is the same network, high school network that I showed you. Okay, distributed according to the grades, and you see that communities have been detected quite accurately. In this case, this is the nested community that has been detected, and the larger community has been detected, and the nested community inside that has been detected. In case of Rocona, 2 separate communities were detected. Okay, in case of LeomCom, the larger community and the nested community has been detected, which is essentially like gives the same information. There are some misclassifications like this one, and Some overlapping nodes have also been detected here. You see that these are the overlapping nodes which are part of 2 or more communities. So in terms of comparison, we again compare this using NMI. So you see that LUAMCOM is able to detect nested communities, and NMI in case of LUAMCOM is much higher as compared to other algorithms which detect nested communities. Okay, so in this case it is 0.816, which is much higher than others. It is second. It is GC has the highest, but it is again second highest in terms of NMI. So LUAMCOM is able to detect nested and overlapping communities, and also you see here in terms of various metrics like partition density, extended modularity, and NMI, we are able to detect the communities in different kind of networks, karate, dolphin, and the performance is above average. You see that L here corresponds to the LUAMCOM. So you see that L is able to perform significantly well across all the networks, which is not the case with other kind of algorithms like ABL, COPRA and all. They are inconsistent. LUAM is consistent. LUAMCOM is consistent. So now the final approach for this is now we hybridize the link granulation and the node granulation that we talked about. First we talked about node centric community detection, then we talked about link centric community detection, and I have told you the effectiveness of each one of these. Now we hybridize both these approaches. Okay. Any questions? I'll just take 2 more minutes. Okay.
Okay, sir.
So, yeah, we just hybridize these 2 approaches and basically detect communities and observe that how accurate or what are the weakness and strengths of the new approach by combining these 2. So again, some experiments are conducted here. Both kind of granulation is taking place, the node centric as well as link centric. Both of them are operating simultaneously in parallel, and finally we are obtaining the communities. So this is the third paper that we are working on, and these are the network data sets that have been experimented. These are nothing but these numbers that you see here are the properties of these networks. Okay, so these properties tell you that these networks do have clusters and all. Okay, so again on human skull network you will see these kind of complexes were detected. Okay, so slightly different, but these are more like in facial complex you see 2 parts, one part with this and one part this. So this is more accurate as compared to the previous one because they are able to detect overlapping communities, which was not possible in case of LUAMCOM. So this node and combining node and link centric granulation leads to further advantages. Okay, in case of high school network also you will see that this result is comparatively better as compared to node centric detection and link centric detection, because we have combined both the approaches. And we are obtaining better results. And this is the quantitative representation of the results in terms of density, partition density, overlapping modularity, and NMI. These are the measures for detecting the accuracy of community detection. And if we see the composite index, we'll see that it is highly consistent. We call the new algorithm as PlugCom. Okay, plural hybridized granularity for hybrid community detection. Okay, plural granular community detection. That is what we call it. And you see that in this case also the performance of PlugCom is higher, and so on. Or for all the networks that we talk about, PlugCom is able to perform significantly. Email network, net science network, Facebook network, PPI network. If you see, the performance is highly consistent, and these are some statistics like the number of iterations that it has taken to converge. In how many iteration convergence has taken place? What is the threshold? I talked about threshold in the case of Rocona. Okay, so these are the threshold which we have determined using sensitivity analysis. And these are all the results. For example, the number of communities detected and the time it has taken for PlugCom to execute on each of these data sets. Okay, so individual timings and the combined timing. So that's about it. Essentially, we have basically this talk was about rough set based computer detection methods. Okay, and we are still working on it. We are working on the advancement of these methods for weighted networks. Right now, these were unweighted. As of now, these are unweighted networks. We are still working on unweighted networks and so on. And as you can see, there are several applications, recommender systems, clinical applications like I talked about in case of brain network, human skull network, recommendation systems I talked about, and various societal and economic applications are there for this kind of approach. So that's about it. Any questions are welcome. I'm open to questions now.
So thank you, sir, for the nice. Yeah. Someone asked to answer, then the session is open for the questions. Yes, sir.
Sir, this is Dr. Devnath Bhattacharya.
Yeah. Hello, Dr. Devnath.
Nice, sir. So how are you, sir? Fine?
Yeah, I am fine. How are you?
Sir, fine. Sir, one thing, when you started the presentation, I observed one nice thing, that is complex structure. Complex.
Yeah.
So, is it going to be complicated one? No. What is the difference then between complicated and complex? Because people wants easy system. So, how you can differentiate complicated and complex?
Yeah. So actually, I didn't show you this slide because I thought that it would be irrelevant. But what is the difference between complicated and complex systems? So this slide will tell you that. So we have three kinds of systems, basically simple, complicated, and complex systems. Okay. So complicated systems are basically man-made systems where mostly machines, when we talk about rocket, railway, all these kind of systems. Here the outcome is very certain, it's predictable. It requires some kind of expertise. For example, if I disassemble a car, it will require some expertise to assemble it again. But the outcome will be predictable, highly uncertain. In case of complex network, the outcome is never certain. Even if you adopt the exact same practices, okay, you won't be certain that you will get the same outcome. Okay. For example, suppose you have two children, you raise both the children with same kind of education, same kind of food, everything. But one child turns out to be a police officer and another one can turn out to be a thief. So that kind of analogy you can see that that is the basic difference between complicated and complex systems.
Great, sir. It's a nice one. It is more than expectations. Thank you, sir.
Yeah. Thank you. So, any other question?
Sir, we have received one question from the online session from the Kauser Ahmad. Can we apply rough set theory in big data analytics?
Yeah, definitely. Rough set theory in case of big data analytics can be applied, but then there would be some generalizations that need to be changed. Okay. For example, what is your system? What is a system that you are talking about? Information systems that you are talking about, that needs to be decided. The principles of similarity that based on which you derive your similarity, that will also need some advancement. Okay. So rough set theory can be applied to big data analytics, but with some generalizations and some advancement. Yeah, I can see this question.
Yes.
Vivek Singh, Dr. Vivek Singh has asked, right?
It's a Dr. Vivek Singh put the moderator. So the question was asked by the Kauser Ahmad.
Kauser Ahmad. Okay.
Yes.
So Kauser, yeah, your answer to your question is yes, but with some generalizations and advancements.
Thank you, sir. So any more question from the participant side? So thank you very much, sir, for your nice talk. We have really enjoyed and hope that researcher working in the application of rough set theory sure extract some idea and apply in their research fields, or open a new idea to collaborate with the medical science and the other what you've discussed right now. As I have heard that you have started your talk from the application of network and nicely created a number of vertices and nodes and edges of the graph theory and connected to the data science, neural network marketing, and boost the human skills. And the last as answers of the Dr. Devnath sir, you have shown the picture of rocket science also. I think is included in the slides.
Yeah.
So, once again, thank you very much, sir, for taking time from your busy schedule and interesting talk in our workshop.
Yeah, thanks for providing me the opportunity.
Thank you.
I hope the talk is useful. Thank you.
Yeah, very much, sir. Thank you. So now our next speaker is joining just in a short minute. So I now has joined. So now I invite Dr. Mahesh Kumar Dubey to introduce our next speaker, Professor Sostak. Over to Dr. Mahesh.
How to say the function is Thank you, Dr. Tiwari. Now, allow me to introduce our distinguished speakers, Professor Alexander Sostak. Professor Sostak was born on 5th December 1948 in Riga, Latvia. He received his diploma in mathematics, University of Latvia, Faculty of Physics and Mathematics in 1971, and candidate of science in the former USSR, Moscow University in 1975. After his PhD, he visited University of Zagreb in Croatia between 1978 to 79 for his postdoc. At the University of Latvia in 1993, he obtained his Dr. Math and Dr. Habibul Math degree. Professor Sostok held position of assistant professor in 1974 to 78 and associate professor from 1978 to 92 and professor since 1993 at the University of Latvia, Faculty of Physics and Mathematics. He served as the head of the Department of Mathematical Analysis at Faculty of Physics and Mathematics, University of Latvia from 2001 to 2007. He is also a leading researcher since 2007 at the Institute of Mathematics and Computer Science of University of Latvia. He is also a full member of the Latvian Academy of Science. Professor Sostak held visiting researcher's position in 1993 at Rhodes University, Grahamstown, Republic of South Africa, and a visiting professor at York University, Toronto, Canada in 2006. He is holder of several scientific grants of Latvia Council of Science in topology and many valued mathematical structures since 1991. He is also the director of the professional program Mathematical Statistics at the University of Latvia from 1999 to 2012. Professor Sostok is a board member of Russian Association of Fuzzy Structure System and Latvian Mathematical Society since 1993. He is served as a president of Latvian Mathematical Society from 1997 to 2001. He is also a board member of European Society for Fuzzy Logic and Technology and the member of program committee of many international conferences in the field of topology, fuzzy structures. Professor Sostak is also a recipient of various awards like Fritz Wohl Prize holder in 2017 and holders of the University of Latvia Annual Award for the establishment of Science School in 2018, to name a few among others. Professor Sostak served as a member of the editorial advisory board of journals like Fuzzy System and Structures, Mathematiki Vesnik, Hesetapi Journal of Mathematics and Statistics, and Iranian Journal of Fuzzy System, and a reviewer of more than 10 scientific journals. His research interest includes general topology, category theory, L-valued topological and algebraic structures, fuzzy structures, and many valued logics. He is author of 2 books and more than 100 research publications in international reputed journals. So far, he has supervised 10 PhD candidates. So now, without further delay, I would like to hand over the session to Professor Sostak. Welcome, sir.
Hello. So, thank you very much. Do you hear me?
Yeah, sir. You are visible and your voice is also clear. You can start now. I am sharing my screen for your slide.
Yes, please. Please.
Yeah.
So, first of all, I would like to thank sincerely Professor Mahesh Dubey for inviting me to participate in this event, to give a talk about the problems that are of interest of me. Thank you also, Professor Mahesh, for a very nice, a very kind introduction, saying kind words about me. Thank you very much. And thank you also, Professor Mahesh, for helping me with technique, because there were some problems for me to install this from my own computer. So here you see the title of my talk, Introduction into Fuzzy Mathematical Morphology. Actually, I will start with classic mathematical morphology and then switch to fuzzy, because I think that most of you are not well aware with this topic. So please, next slide, please. Next slide. Mukesh, do you hear me?
Yeah, Professor, I have moved to next slide.
Yes, we hear you.
Yes. So thank you. So here you see the contents of my talk. I'll start with history of creation of mathematical morphology, then the relations of mathematical morphology and image processing, now at present very actual, very important link. Then, as I told, a large part of my talk will be devoted to classical mathematical morphology. Then I switch to fuzzy and start with the fuzzy mathematical morphology, but in classic version when it is in Euclidean space. And then at the end, I'll say some words about abstract approaches to fuzzy mathematical morphology. So please, next slide. So here, the title of the next of my first section, History of Creation of Mathematical Morphology. In this case, we can almost precisely say the date. It is the very beginning of 60s of the previous century, and it is quite seldom situation when we can clearly say who are the creator of the science. There are not so many cases when we can directly say that this person is the inventor, the founder of the theory. No, one example of what we can about say science when inventor founder is known, it is set theory. Cantor is without doubt invent, and this is also the case that the founders of mathematical morphology are engineers. George Matheron, here you see his dates of his life, and his student Jean Serrat, both of them are French mathematicians, and Matheron was working as a mining engineer and studied problems of mining problems by methods of so-called geostatistics. I shall say some words a little later about it. And Jean Serrat, originally he was a student of Gestalt psychology, so he was a kind of humanitarian science. But when he was a PhD student, he was invited just to earn some money to make some investigation in the field very actual at the time, mining, analysis of mining patterns. And this also led him to geostatistics and his collaboration with Professor Matheron. So please be so kind. The next. So please then, yes. And only some words about what it is geostatistics. It is a science using statistical methods to apply them, to use them in mining problems and some other geological geodesical problems. The idea is that a researcher takes some pattern, some sample, and studies it, and the idea is that the nearby pattern samples taken somewhere in the area will be approximately similar. And this well works for in many cases. And so this science, applied science, developed and had real importance. But it didn't work in Serra's case. So please, next slide. Next picture. And what is the problem? The problem was that in the area when this research was conducted, there was very strong calcite influence. Small pieces of calcite completely change situation. You can take a sample in one place and it will be full. It seems the sample is very small. They can be more than a half of calcite ingredients, while nearby will be pure iron. So this rose problems to use classical geostatistics methods in this concrete, this special research, and led both scientists to think of some other possible approach to solve these problems. So please, the next. So, and the idea of Serra, fundamental idea of Serra, was to start from to make a shape of the whole structure, not to take separate samples, but make focus on the whole structure of the object, and to start, as here is written, I write, to start with some small structural element, to make it interact with the whole image, to interact with the whole picture of what they got about the situation, and then to study how these small pieces influence the general picture of the general picture to be studied. And this interaction of these small pieces, they are called structuring element, yes, in this case. So how these structuring elements closes, smoothen, occasion holes and protrusions that appear in the image. So these holes and made by some element which is in this case calcite mainly, which is not needed, which is not typical for the whole picture. Okay, please, the next slide, the next picture. Now we come to, I shall say some words about image analysis, although it is not the main topic of this presentation, but some words must be told because it is really now applied very, very seriously. So please, the next. So image processing is a method to perform some operations on an image in order to get an enhanced image and or to extract some useful information from the image. Image processing basically includes the following 3 steps. First of all, of course, the image must be inputted using some equipment. Then the main, at least the central stage, to analyze and make some manipulation with the image. And finally, to get output where we, in the result, we see the important features which we either the whole image improved or somehow reworked, or the most important features what are interested for the researcher. And there are, speaking about image processing, usually they're distinguished two different types. Image analog image processing and digital. No, actually, what we are doing is related to digital by using possible using of computer, similar technique, but some words about analog image. As an example, I can say that some picture can be studied by some experts, and one say that this is like this, another says that important moment of the picture is like this, and then they somehow the result the result modified it. But in the case of digital processing, this is usually done automatically. And please the next slide. The next. Yes, and some more words about image processing. There can be two mathematical and two, let's say, approaches which do not use mathematics. Heuristic, so just by intuition, a researcher says that it must look like this, and so on. And other experimental and statistical, making experiments several times, make some, the researcher makes some conclusions. But for us, of course, I'm interested in mathematical methods, and there are two, at least to my knowledge, two. One, which is based on signal processing and information theory. It interprets an image as combination of sinusoidal frequencies. So it focuses on information taken on separate pixels, and then combines from them the whole picture. But another method based on mathematical morphology focuses on another issues. So please, next picture. So here is written the main reason of mathematical morphology. So the purpose of image analysis by mathematical morphology is to find special object, not separate moments, but make focus on the spatial, on the whole image. Therefore, image contains geometrical shapes and also, in this case, color profiles. This, again, the idea coming from Serrat that all these special forms and the colors can be investigated by their interaction with other shapes and color profiles, what are presented by appropriately chosen structuring elements. This makes the use of mathematical morphological approach especially relevant in situations where color images correspond to significant material data, medical diagnostics, microscopy, robotics. So in medical diagnostics, the typical situation is that we do not need, we are not interested in the whole image. We're interested in some parts of the whole image which are which have some problems, some illness or some destruction. So this is exactly what mathematical morphology methods can do best. Yes. Okay. Thank you. So now the next slide. So now we come to the classic, and you can go the next. So what is the mathematical situation? We start with a set in a Euclidean space. I'm sorry, here A belongs actually must be also at least read several times. I haven't noticed that here must be not belongs, but is a subset, and here also. So A is some subset of Euclidean space, or usually in this theory, A is a subset of digital plane containing consisting of all numbers with natural real coordinates. And now we want to modify it to study this image by means of interacting with some other element. And in this case, we take a subset B, which is in both cases either A is in Z power n or in n A power n. Usually B is taken in R power n because it is intuitively it is small, and so we cannot use only integers. And now we use translation B by Y by this formula. So here, I don't know why, but often this equality looks like minus. It is, of course, equality. This is equality and this is equality. So what is tau P by? This is the transition of B along vector y, So here are two equivalent formulas. Probably the more easiest to understand is this one. We have all x, which can be obtained by y plus some element from B. So it is a set transition, and the idea is, can you a little up show the same, but a little move up, a little. No, the previous slide, but a little up. Okay, but this is really needed. Is it possible to move this slide a little up? You can hide this part. You can hide. No, see, we must go the previous slide. So I don't know how to manage, because the last. Do you see this last line? I don't see it, but without it, I cannot explain what is these basic operators.
Is it visible now, Professor?
I say now we don't see the whole picture. The last line is not seen. Can you move somehow a little higher to see the last line?
Yes, erosion is given. This is the slide, sir.
Yes, but you don't see this. What I see now, we define the basic operators of mathematical.
Defines operators of mathematics, dilation and erosion. You have defined dilation DAB equal to Y such that TYB intersection A is non-empty, and the erosion is defined.
Yes, you see.
Mahesh, can you make it to full screen? Go to view and there will be option to make this slide to full screen. That will be better.
This is full screen side, I think. This is full screen side.
Okay, but if you see it, you do. So my question is, do you see the last line?
Yeah. Is it visible now, Professor?
Yes. So we get dilation by in order that it intersects A, and erosion, we find those movement of B, which move this B inside A. So this way we get two formulas for dilation and for erosion. No, I hope you see this last line. Unfortunately, in my case, it is not so seen, but okay, we can go to the next slide. But problem is that I cannot see the whole, but okay, at least what we see now, the properties of these operators are quite natural and easy to be proved. So dilation, both of these operations become increase if A increases. Because from the definition, it is clear that intersection with a smaller element implies intersection with a bigger element. And also with erosion, if we get inside smaller, then we get also inside bigger. But in case for changing element B, which is not so practically important, the situation is opposite, because the bigger element can hide, can smoothen larger holes, and leads to erosion becomes smaller. And so another, it is quite natural that erosion is less than dilation, but in case when the center of the linear space belongs to, is in this structuring element, then erosion is inside A, and dilation is inside, and A is inside dilation. So in this sense, it is something like interior and closure if you compare with topology, but this topological aspect will be also further, but at present, so I just mention it. So please, next slide. Important properties of these operators are what is can be called semi-continuity. If no, usually we change or work with images. So with A, B usually is fixed, and so in the formulas it appears as a fixed element. But if we are changing A, then the situation is such. If we take intersection of not important how many images AI and take then the erosion of the this intersected image, then it's just the intersection of erosions. So continuity from the up, going from intersection to intersected sets. And for dilation is vice versa, because we are somehow uniting these images, interacted images, and so dilation of a union of images is equal to union of dilations of these images. So this is also important properties that will be repeated also in the following cases. So please, the next. Another important property, important in now I'm speaking about trees, but all these features will appear, will be repeated also in fire case. So these operations are dual. What means duality? Since everything happens in a space, Rn or some other, I denote it just X in some cases, but on this slide it is Rn, R power n. So complement is X minus A, the complement of A. And dilation can be obtained by complement of erosion and from complement of image structured by B. You see the upper formula and the fourth one. The fourth one says the same, but I think it is more visible. And erosion, also erosion is a complement of dilation of complement of image structured by B. And in the same is in the last formula. Okay, now we can go to next. So what in the next also important property, this dilation in some situations, not in this one, could mean the work with such formula, DAB equals C, then A equals ECB. But in this situation, it doesn't work. Examples can be very easily constructed, but is theorem not very difficult, but very important, that if dilation of A, always started by dilation of A is inside C, then A is erosion of C. So this property is mathematically very important. It is called, in this we say that this pair makes an adjunction. Adjunction, the pair is injunctive, and E is lower adjunctive and D is upper. Probably who doesn't know this concept, it is closely related to Galois relation, but it looks similar, but then there is some change of these objects, C and B. But for us, it is important to leave B as a structured element on the right side. Okay, thank you. So please, next. On the basis of operators erosion and dilation, actually these operators are the principal ones, but the main work is not with them, but with so-called derived elements. And derived elements is closing of closing and opening. Closing is defined this way. B is, in this situation, we need to apply the opposite, the reflective of B. So B consists of some elements, but minus X, all these minus X constitute minus B. Now here is a very trivial example. And closing is defined by taking, first of all, dilation A of A, and then taking erosion, but structured by minus B. And opening is, at the beginning, we take interaction, and then erosion A of A, and then dilation of this erosion, but structured by minus B. This minus B can be a little disturbing, but usually B is taken with center of zero element, so in the center of the coordinate system. And usually it is taken in practical work, it's taken as something symmetric, something like a cube with center zero, or a ball with center zero, or some other. So in these situations, this minus B doesn't appear, just B, and then the formula look in many situations easier. And here is, in the upper part of the slide is written exactly this situation. So please, the next slide. And the properties of these operators are monotonicity. One, of course, can expect. The larger, closer, the larger is larger. Here, A always is inside of CAB. So the problems which appeared when we're speaking about dilation, that we needed to have zero in B, zero element in B. Here it is overcome again because the more smoother structure of closing than of erosion. And the next very important, and in some sense I would like to emphasize it, that idempotency, 2 times using closing, we get the same operator. So this means that we get something like topology, but actually it is called pre-topology, because the definition of a closure of a space asks that the closure of a union is equal to the union of closures. Here it doesn't work, and the examples are quite easy and natural, but we get so-called pre-topology. So the axiom of union of two closed sets. If we define closed sets, those which are invariant in respect of closure, then it will be so-called pretopology, all axioms okay, but not the union. And now, please, the next slide. So here in the first line, of course, here must be O, not C. It's usual mistake when something is done by pasting, so the C is instead of O. But the second is okay in O A B. So opening of A structured by B is inside A, and again idempotency. So if we use topological terminology, or open and closure make so-called the pretopological structure. Why pretopological? I already explained, because the union in case of opening intersection axiom doesn't are not valid, but D, because closure and opening are related in such a way that we cannot apply them immediately together. Okay, then please, the next slide. Also, closing opening duality, complement of closure. I comment the second line, complement of a or again mistake, not erosions. Here must be C. Here also must be C in both first and second line, not crisp A, but crisp C. So opening is a complement of opening is closure of complement complement of A. And the next property also says naturally that opening is, as we intuitively mean, some kind of interior of A, and C is some kind of neighbor, A with neighborhood, with its neighbor, something like closure. Okay, thank you. Then the next. So these operations are given in such a way that they are very closely related to so-called Minkowski arithmetics. Minkowski is a German mathematician. In the slide you see his dates of life, and he is known for different results, for different important things he has done. For example, he is known as creator of so-called geometry of numbers. Also, he is known as giving a some geometrical interpretation of Einstein's theory of relativity, and some also in functional analysis Minkowski operator. But I mention him because he's the operators of Minkowski addition and subtraction are closely related to our. You see, the first line says this addition written in the terms of mathematical morphology, and also it can be also very nice written as sum of x and y from x and y from b. So, the subtraction is also well behaves with our Rosen definition, and here I repeat the same definition, but it cannot be rewritten as nice as in case of addition. As we see here are examples, and so it is in this sense algebra of by arithmetics, let's say, Minkov's issues is different from classical arithmetics. But we do not need to go into details of this. But I needed to emphasize this moment since it will be used also in future in the next slide. So please, the next slide. Yes, and here if we admit that B is minus B, then these operators are written very, very clearly by means of Minkowski operators: dilation, Rosen, closure, and opening. In this case, the picture looks well. Now come to Euclidean case, the notation F are and all fuzzy subsets of Euclidean space, and we can go further. Now let's think what is object now, and what is the object to play the role of an image, and what is the structural element which produce operation of erosion, dilation, and so on. And the answer is that in this case we can take fuzzy sets, and we can take also usual sets. Again, here situation will be different even if they are ordinary sets, and these A and B can be colored or gray. So please next. And now to understand the idea how the fuzzy approach can be obtained, we extend Minkowski addition for fuzzy case. I don't know who was the first to define in this way, but at least some references will appear at the end of the slides, in one of the last slides. And namely, addition is defined in this way. Those who feel the mathematical logic will see the analogy with the AB as it is in crisp case. Yes, so conjunction is instead of and this is the kind of transition belonging to element I minus x to A. So the structure is quite natural if we feel the feel how fuzzy operations are obtained by means of applying fuzzy logic elements. Please, then the next one. So here is definition of dilation first. When we have plus, this O plus, then we can define dilation in analogy as it was done before. So if B is any, then here must be minus. If B is structured, then here is just B, so very nice. And explicitly, this is written, not important, B is minus or not, but in the formula it will appear in this way. Now, please, the next one. Fuzzy subtraction here is written. No, I shan't comment it. It's also in a natural way, and we can go to next slide. And fuzzy erosion is defined also in analogy as it was in classical case, and here is the formula, explicit formula, how it can be obtained, how it can be got. And please, the next. The next, again, important properties of erosion and dilation are similar to those ones which were in crisp case. Semi-continuity from above, upper semi-continuity for erosion, and lower semi-continuity from below for dilation. Again, repeat the same properties, and this is for the theory, of course, very good. So please, the next one. Also duality. Now here, complement is used. Complement for a fuzzy set is in the upper line is written. It is 1 minus a. A is a function here. 1 is also a function. So it is a function in R power n. And dilation behaves in the same way as it was in crisp case. So I shan't repeat everything. I only comment the last two formulas. Then now complement is 1 minus and 1 minus. And for any A, B in fuzzy sets. So, okay, then please the next. The next, again, the problem which I discussed quite much, not much, but it's mentioned about crisp case. Again, no such implication. We cannot just switch the arguments. But the last, the theorem above shows very important property which, similar as in crisp case, is called adjunctness, and the precise definition will appear at the end of my talk, but I think you can feel already the idea what this means. It means this type of behavior of two operators. Okay, our time is going very fast, and so please the next one. Now the situation very similar to crisp, since we have seen everything in crisp. Same closure and opening are closing and opening are defined in a similar way. Again, if B is any, then minus B. If not, if symmetric, then just B. And here explicit formula. Since here are two times these fuzzy operators, so formula becomes more complicated. So soup, as usually in fuzzy interpretation, instead of union in crisp, in fuzzy instead of intersection in case of crisp, and this for logically it stands or either this or this, and here is the comments to compare with crisp case. So please next. Yes, now I am going to abstract approach, but before I go, I would like to say, it is not reflected on the slide, I must say that there are now crisp mathematical morphology is very well applied now in practical tasks of image processing. So there are probably hundreds, even more papers, different results, and also in some attempts to make color use of proceeding of color images using crisp morphology. But recently there appeared some, no, at least I know 3 papers where methods of fuzzy mathematical morphology are applied, and quite successful, exactly in papers known to me are related to morphological methods in medical diagnosis and in biological microscopic image processing. So this is just to say some words about the possible applications. I am not very strong in applications, but it is for me also interesting to find, and I see that these methods are seriously used in this, at least in these papers, to get some results. And now, please, the abstract. So, going to the abstract situation, we have now to analyze what we had up to now. We had 2 operators in 2 situations. One situation where crisp sets P X are all crisp subset of X, and Fx are all fuzzy subset of X. And so they were changing, mapping one crisp set into another or fuzzy into another. And what if we want to generalize them, what are the main properties? I before try to emphasize them. Upper and lower semi-continuity, respectively, for one or another operator, duality always was, and conjunctness. And now if we want to make an abstract approach, we must think about this property. So please, next slide. So Px, what was on the previous slide, and Fx, their important features are that they are lattices. That what is lattice? I think most of you know, but I remind. So some set with a relation. This relation is reflexive, antisymmetric, and transitive. A less than B, B less than equal than C, then S, A less than equal than C. I think it is quite natural, and you see that, I hope you see that all these properties are in lattices Px and Fx. If we comment less or equal for subsets, for sets subset, and for fuzzy, again, exactly as functions, less less or equal. So please, the next slide. Yes, no, here definition what is upper bound of A and B. Here is precise definition, but idea is that we look for the smallest one, which is larger than A and larger than B. And in a similar way, define the lower bound. We are looking for the larger one, which is less or equal, larger or equal than less or equal than A and B. And partially ordered set is called a lattice if any two elements have upper and lower bounds. And the examples which we have, and they are indeed the simplest one, all subsets of Euclidean space under inclusion, and all subsets, fuzzy subsets of R power n under this comparison as functions. Okay, thank you. Next one. And one more definition, upper bound for family. So here we are looking for the smallest one, which is larger than all of elements in M, and lower bound, we're looking for the largest one, which is less or equal than all of them. I think this definition known, and for any case I gave here on the slide. So please, next one. So now is the definition. The definition, abstract definition, what we can have as a abstract erosion and dilation. A mapping is called an erosion if it is just upper semi-continuous. We define in a very axiomatic way. Dilation, vice versa, it must be lower semi-continuous, yes, so lower semi-continuous. The formula is given, so I won't say anything more. So be so kind to get the next. So now we now define completely, abstractly, and independently erosion and dilation. One, in our case, will go from M into L. We have two lattices. Probably I haven't said it yet, so we can. No, I told, yes. No, of course, it can be one lattice, but generally it can be two different lattices. M and L. Erosion goes from M to L, and dilation from L to M. And then the pair is called an adjunction if, and now you see the formula which twice already similar to this formula, twice appeared in my presentation, in case of crisp and fuzzy morphology. And so please go the next slide. And now theorem that although this definition was very abstract, these definitions have very good, actually, not occasionally. Namely, theorem says, I reproduce some of statements. If delta is erosion and where epsilon is delta is dilation, erosion is where epsilon is erosion, and they are defined independently. But if they make a junction, sorry, I'm not correct. Just given some mappings without any properties. without any properties, delta and epsilon. But we know only that they make an injunction. Then it can be already proved that in this case, delta is dilation according to the previous definition, and epsilon is erosion. And second, if we have now already dilation, we know that it is dilation, then there is unique erosion which makes epsilon delta as an adjunction. Further, similar with erosion. If we have erosion, then there exists a unique dilation such that it is a junction. So you see the behavior is quite good, and some other properties showing that these abstractly defined concepts are nevertheless very well incorporate the information we had in our primary examples of crisp and fuzzy morphology. Please, the next. And another properties. If we have now two operators, and in such a way that we know that they make an adjunction, we know already that in this case epsilon will be erosion, delta will be dilations, but the theorem says that in this case, if delta 1 less or equal than delta 2, this means exactly that epsilon erosion is vice versa. And now if we have a family of dilation and erosions such that all of them are junctions, then we can make a combined junction by taking infimum mean of all erosions and supremum of all dilations. So please, the next. Yes, and now two examples which show how we can get some real operations of this type, abstract operations, but from some real situation. If we have two sets x and y, and if we have relation R, then we can define dilation as all y for which exists x in x such that x is in attitude R with y. Defining this way dilation. If you remember, this is quite similar to, probably not quite similar, but reminds definition of dilation already in crisp case. And similar, not similar, but in an analogous way, we define erosion, all y, all x, such that for all y, which are related in this way, it follows that y is in B. Here is B. Is E is in B. Misprint. And this is example that it will be erosion dilation pair on the pair of lattices already known to us, but the difference is that we do not use here linear structure, and that we can have different sets x and y. And next, I think the next will be the last of before conclusion. So similar, if we are starting with a fuzzy relation, then in a similar way we define, but logically similar way, we define dilation in this way and erosion in this way, and we get a junction pair of lattices fx and f by y. So the way how to crisp from situation on sets to go to abstract situation on lattices. I missed here the topic about duality. I emphasize the importance of this property. I especially missed this moment because it will need at least 20 minutes more to explain, because there we need some more details. And so I must say that there is research in this direction, and under some assumption it will be also satisfy problem of delation of duality, but I don't touch it here. Then now please the next slide. Yes, here is on two slides here is the material I used. The history is very well written in this HTTP. I used all information I told about history are taken from this issue, so you can find there much more and more present. Then important material which I used in one way or another, and I would like to emphasize this Bytes fundamental work, Isabella's blog and her co-authors chapters on mathematical morphology. Certainly see also the next ones, and please one more slide. The next. Yes, here are some more. In particular, Sarah paper, one of original papers, Jean Serra's paper on image analysis. Our, with my colleague, work on fuzzy relation mathematical morphology. It mainly relates to the last slide. And certainly there can be much more, but this is the main what I used in this presentation without giving every time what was used for each one slide. It would be too boring. And now please the conclusion. Thank you for your interest, and I am really thankful that you came to listen, and I am sorry that due to technical problems it was a little complicated. I am sitting here, slides are shown kindly by from India, from Indian University. I am in Latvia, on the near the sea. You are in India, but anyway, thank you for your attention, and hope you will use this information somewhere, sometime, at least some of you. Thank you very much.
Thank you, Professor, for a thought-provoking talk on such an interesting topic. Now, I open the sessions from audience to ask their queries from the professors.
I have one question.
Yeah.
Yeah. As in the last slide, you have defined the concept of erosion and dilation in the sense of fuzzy relational mathematical morphology. Like you have taken a relation R over the two sets X and Y, and where the erosion and dilation are the function from power set of X, fuzzy set of X to the fuzzy set of Y. So is it possible that we can take it as a from rather than considering the two set X and Y, just having a set only one set X, and we can define erosion and dilation as a function from fuzzy set X to the fuzzy set X, and we can connect it with the notion of closure and interior operator in the fuzzy topology.
No, if I understand your question well, yes, it is. It will be. the erosion and dilation will look like topological operators. Yes, but as I told, there will be not one axiom verified about closure. The union of two closed sets need to be closed, and the intersection of two open need to be open. Otherwise, it is all other axioms are, and this structure is known in topology. If I probably didn't understand your question correctly.
Okay, thank you.
Okay, any queries from other?
There is a question in the chat box.
Yeah, from the live sections, Dr. Narmada asks, can you give one real life application of the fuzzy mathematical morphology, sir?
Sorry, I didn't understand. Your question is?
Can you give one real life application of fuzzy mathematical morphology?
Application?
Yes, sir.
Applications. I know several works, but I cannot demonstrate them now. But if you are interested, you can send me your email, and I'll send you several, in particular in medical diagnostic color. In biology known to me, also some of where colors are important. There were some papers where the research of segmentation of colors was so I have quite many examples, but I cannot demonstrate you now on the screen. So please send me your email, and I'll send you several, and probably even with my comments, what I think about.
Thank you very much, sir.
Okay, once again, thank you, professors, for accepting my request and taking time from our busy schedule to deliver your lectures on our workshop. Thank you so much, Professor.
Thank you very much. Thank you. Thank you. It was a pleasure for me to meet with you online, being so far apart geographically, probably some 5,000 kilometers. We would communicate.
Yes,
Thank
Professor,
you.
when situation is normal, then we call you to come in my country and visit some good places. We plan in next year also.
Thank you. Thank you.
Thank you, Professor. So thank you to all participants. This is all about today. We will meet next tomorrow at a scheduled time of lectures. Thank you once again to all. See you, Professor.
Thank you, sir.